In this video, we're going to see that integration by parts can sometimes be a little bit more annoying than the first couple videos maybe gave away. As you see up here in the notes, sometimes we may actually need to apply the integration by parts formula more than once for a given question. To kind of see how this would work, let's take a look at example number 3. Now, I have to make a selection here for, again, what I want to be u and what I want to be v. Well, I'm going to go ahead and imagine separating it out in the following way. I'm going to pick u to be this x squared because I think it's really easy to take derivatives of polynomials, even easier than doing their antiderivatives. And I'll let the other portion over here represent my dv. So I'll say again, I'm going to have u be equal to x squared, and, oops, that'll be my dx included in that as well. My dv will be equal to my sine of x dx. So, if I was to select this, then my du would be equal to 2x dx, and my v, let's see, sine would come from negative cosine of x. Okay, so if this is what I have, I can start to see that using integration by parts, my integral of my x squared sine of x dx would be equal to, and I'm going to have my u times my v, so notice that's a negative x squared cosine x, minus my integral of v, which is my cosine of x. Notice I'm going to take that negative there, instead of putting it on the inside, I'm going to pull it right to the outside and change that to a plus, and then I should have du, which is my 2x dx. Now keep in mind that our goal every time that we apply this integration by parts formula is to see that this new integral is a bit easier to work with than what I started with. So again, I don't know how exactly I'm going to find this integral over here. I can use any of the techniques that we talked about in that first video at the start of this section. I can try to see, is this a derivative rule that I know from Calc 1? No, I don't really remember this as any complete derivative rule. Is there any algebra I can do to rewrite this? Can I like factor something or simplify something down? Or no, not really. And can I do a u substitution? No, that maybe doesn't seem to fit well, but I could see, could I imagine this again as a u and a v? And start to think about using integration by parts again. So I'm going to go ahead over here and I'm just going to zoom in on it again. What is something in here that would be easy to take a derivative of? Well, again, I'm going to say, how about the polynomial, right? Those are always easy to take derivatives of. And then maybe I can do the trig function again as the thing to do an antiderivative of. So if u is 2x and dv is the cosine of x dx, then du should just be equal to 2 dx. V should be equal to positive sine x, right? Derivative of sine makes cosine. So if I have this, then I'm going to go ahead, I'm going to kind of carry down my equal sign from up above. I'm going to keep everything else here the same. What I like to do is to put up some big brackets right away because I'm going to replace this integral here, and I want to make sure that if there was any subtraction out front or a number out front or anything like that, that I protected what I have on the inside from what might need to be distributed into it. So I always like to put my new stuff here in a big set of brackets. So I'm going to have here again a u times a v, so that's going to be 2x sine of x. And then it's supposed to be minus, and gosh, I hope this integral's easier, v du. So that's going to be sine of x times 2 dx. Close that off. Now, fortunately here, there's nothing really to distribute in. So while it was good to put these brackets up initially, they don't really matter much anymore. Now this may not happen in every question, so that's why I would encourage you to always kind of have those brackets in place. But now notice if I can just focus on this final integral, I'll be good to go. I'll see that the 2 is a constant, and so I could actually just go ahead and pull that out. And so I really just need to know, oh, look at that, something easy. The antiderivative of just the sign. So I can go ahead and re-express that as just, let's see, where does the sign come from? It comes from the negative cosine of x. I'll just go take that negative and put it right here and change that back to positive. Of course, since it was an indefinite integral at the start, don't forget at the back, plus c. And I have myself a perfectly good answer. That's fantastic. And of course, it would be easy to check to see if we were right. How would you check it? Well, you'd just go ahead and compute a derivative of what we just boxed there. And as long as it returns you back to our x squared sine of x, you know you must be correct. That can seem like a lot of work, but every so often I would encourage you to try that just to make sure that what you're doing makes sense, especially in the moments when you have time to practice. Maybe in the middle of an exam, that's not the best use of your time, but in other instances, like on a worksheet or as you're doing some other sort of assessment, like, hey, you got time, so why not actually give it a shot? You'll actually cherish the moment here as we move into later sections when checking our work becomes much, much harder. Now, unfortunately, the news gets even worse. We saw in this question that we had to actually use integration by parts 2 different times, right? We had to use it once up here and once down here. It's possible, though, to actually write a question where you could be required to use integration by parts 3 consecutive times in a row, or even 4 consecutive times in a row. In fact, I can design a question where you could be required to do integration by parts as many times as I want. I can make you do integration by parts 1,000,000,000 times in a row. Now, I'm probably not going to do that for a test, but I actually think it would be very reasonable for me to ask you in an exam to do something like an integration by parts 10 times in a row. Now that may sound completely absurd at first, but this is why our next several videos are going to start to talk about the idea of how I might be able to shortcut this idea of integrating by parts under very select circumstances. And with that, I might be able to speed up the process at which I can arrive at my antiderivative.